Hi there, this is Lucius Laframboise from QESuite. Today we're going to talk about capability. This is going to be an in-depth introduction to CP, Cpk, Pp, and Ppk, what we would otherwise call capability. So in this introduction, we're really just going to talk about what do these values mean, how do we derive them, how do we calculate them, and why do we get certain values for passing and failing. So, as engineers, we often ask ourselves this question: how likely is our process to produce parts within specification? This is our big question. We want to know if the process that we created, that we are validating, is capable of producing parts within specification. And very importantly, our customers want to know the risk of us producing an out-of-spec part just as much as we want to know, because our customers don't want to pay for things down the line just as much as we don't, okay? So how do we do this? How do we answer this question? How likely is our process to produce parts within specification? The answer is statistics. As engineers, we like values that are pass-fail. We don't necessarily like continuous. We want discrete yes, no, pass, fail. Capability indices are an example of this because we can set a critical value that if our capability is above that critical value, then we can get, when it's passing. If it's below that critical value, it is failing. So generally in capability, that critical value is 1.33. Now there's a reason for that, and that'll be later in this video. And throughout the process, we're slowly going to build up to ask that question of why is 1.33? That 1.33 is going to, if you don't know why that's the number, going through this video will change everything for you when it comes to capability. So what are these capability indices? Well, you've got CP, Cpk, Pp, and Ppk. And they're all calculated differently and provide slightly different information, but they're all used for the same general purpose. And that is to estimate the probability of an out-of-spec part. So when we calculate the capability indices, especially Cpk and Ppk, we're actually calculating a modified probability of producing an out-of-spec part. And in the mathematical proof, I'll show you what that means a little more. The problem is we can only use these capability indices if and only if proper assumptions can be made. So what are the assumptions for capability? Well, the first is that the sampling is random and representative of the population. This is because if your sample is not representative of the population, then your capability isn't telling you about the population. Generally, your sample size needs to be greater than or equal to 30. The reason for that is partially because of the second assumption, that the data is normally distributed. Because of the central limit theorem and the of normality, we know that, and there's a huge math proof, maybe someday we'll get into this, but all you need to know right now is that past n equals 30, the the variance generally goes down to a negligible amount if your data follows a normal distribution. After 30, the variance is negligible. It's a really, really cool thing. I highly recommend you looking it up, but that would be why it has to be greater than or equal to 30 in most cases. But the second reason we need the data to be normally distributed is because that's actually how we get the formulas for capability. What do I mean by that? Well, now we start the meat of this video, which is the actual mathematics behind capability. To start, let's learn about the normal distribution. The normal distribution is part of probability distribution theory, and what we're really focused on in here is the StDev, the continuous distribution function. It follows this formula here, where ERF is the Gaussian error function of x, the actual value we want to evaluate, then mu being the mean, and sigma being the standard deviation. So what is f of x? Well, f of x is the probability of a random value less than or equal to x occurring. Okay? So if we evaluate the continuous distribution function, the StDev, of x, we then return with the standard deviation of sigma and the mean of mu, we get the probability of a value less than or equal to x occurring. So what does that have to do with capability? Well, if f of x is the probability of a random value less than or equal to x occurring, then f of the lower spec limit is the probability of a dimension less than or equal to the lower spec limit occurring, the probability of x less than or equal to LSL. We also know that 1 minus f of USL is the probability of a dimension greater than or equal to, we also know that 1 minus f of USL is the probability of a dimension greater than USL. That's the probability of x is greater than USL. So, what can we do? Well, if we know that the probability of x being less than or equal to LSL is the probability of a failing value less than the lower spec limit. Anything less than your lower spec limit is a failing value. So now we know that this is the probability of failing below the spec limits. And the probability of x is greater than upper spec limit is the probability of failing on the upper side of our tolerance. So if we add those two probabilities together, we get the probability of an out of spec condition. Okay, so now we know that if the data is normally distributed, we can use the cumulative distribution function of the normal distribution to calculate the probability of getting an out of spec condition. So what we're going to now do is kind of sidestep a little bit and learn about the standard normal distribution. The standard normal distribution is a normal distribution with sigma 1, so standard deviation of 1, and mean or mu of 0. We use this because any normal distribution can be represented by the standard normal distribution using z-scores. It's a way of standardizing all of your values so that you really only need to care about one set of numbers. Really, generally, in most scenarios in engineering, we care about what's called 6 sigma. I'm sure you've heard of that. And that means that we really care. We want to be between -3 and +3 standard deviations of the mean. And a standard normal distribution, that means from -3 to 3. That's why we use the standard normal distribution. Pretty sweet, huh? So to use the standard normal distribution, instead of plugging x in, we would plug in z, where z is your z-score, calculated by x minus mu over the standard deviation. This allows you to standardize and basically pull out our x minus mu over standard deviation in the cumulative distribution function here, in the CDF here, and just have 1/2 times 1 plus the error function of z over square root of 2. It standardizes it, right? Okay, so what happens if we substitute our upper spec limit and our lower spec limit for x? Well, the z-score of the lower spec limit is LSL minus mu over sigma. We can plug that in, and we can get the probability of failing below the tolerance. If we plug in the upper spec limit, we can then use that z to retrieve the probability of failing above. Again, we know that those add together to the probability of an out of spec condition. Now this kind of looks like we took a bunch of extra steps. We already had this. Why would we want to calculate out x minus mu over sigma? We already had this. Well, it's because this shifts everything. It transforms all of the data to centered around 0 with the standard deviation of 1. And that's how we get capability. Capability is a modified z-score. Let me show you. So if you take a look at Cp and Pp, they kind of look like z-scores, right? You have a value minus another value over your standard deviation. It's your upper spec limit minus your lower spec limit. But if you look at your Cpk and your Ppk, it looks almost exactly like a z-score, except you're taking the min of 2 z-scores. Your spec limit minus mu over your standard deviation. So what's the difference? Why are we calculating these slightly different? Well, you'll notice the difference between the C's and the P's is because of this sigma and this S. The sigma stands for your within standard deviation, which is a beast. It's not that bad to calculate, but it sure isn't fun like the sample standard deviation, because this involves some unbiasing constants. Check back later, we will have a video on that. But this S is your sample standard deviation, or your simple standard deviation, to throw a joke in there. This is what you're used to. This is taking the absolute value, the sum of the absolute values of all of your values deviation, and taking it over the degrees of freedom, which in this case, because it's the sample, is n minus 1. So what's the difference between CP and PP and CPK and PPK? Well, CP and PP are just a comparison of process variation to tolerance width. So it doesn't care where your values are located. It's not really calculating the probability of a failing value. All it says is your process variation compared to your tolerance. So a very high value means that your tolerance width is a lot bigger than your variation. But you can have a passing CP and PP, like an incredibly high value for each of them, and still fail capability. Because in general, we mainly care about CPK and PPK, because that's your actual probability of an out-of-spec condition. So what do I mean by that? Well, if we look at CPK and PPK, they're actually modified z-scores. Actually, your spec limit minus mu and your mu minus spec limit. That's just a way of taking an absolute value, because your mu, in order to have a passing capability, greater than 1.33, your mean has to be less than the upper spec and greater than the lower spec. Otherwise, you'll get a negative value. Negative means fail because it's not greater than your critical value. Okay. PPK and CPK, we know the difference between C and P. It's the standard deviation you use and how that's calculated. But why the min? Well, it's because z-scores closer to 0 are more likely. If you have the z of your spec limit being the probability of out of spec, now we no longer need both sides anymore, because all we care is, do we fail? So if we take the most likely, the one that's closer to 0, then we know that that is the most likely to happen. Okay? Because they're both absolute value, we can take the min to get the closest to 0. But why the 3 sigma? Why the 3s? It's because you've heard of 6 sigma, lean 6 sigma. We've already talked about it a little bit in here. And that's because your process spread is represented by 6 sigma. That means that we really only care what happens between -3 and +3 sigma. That's where we want everything to be. And when we calculate the critical value of 1.33 and show what that actually means, you'll then understand what 6 sigma means and why 6 sigma. The other reason that it's included in your actual capability indices calculation is because it scales it. It makes our indices smaller and more manageable. It gives them recognizable values like 1.33. Okay, so let's actually do some calculation here. So we know that our C or PPK, for now we're just going to use STD to mean standard deviation and the star to be either C or P, because they both show the same thing, just slightly different because of the different standard deviation calculations. So we know that the absolute value of the spec limit minus mu, because now it can be either U or L, upper or lower, because all we care about is which one's more likely to fail, over 3 times the standard deviation. So we can break the 1/3 out. We know that this here is actually a z-score. So we know that our capability index, either one, is going to be 1/3 of its z-score. So we can take our capability indices, multiply it by 3, and get the z-score. Okay? Then we can calculate the probability of z using some software like Excel. Okay? So what we're going to do is, if you're in Excel, use equals norm.s.dist of z, and then put in true to get the cumulative distribution function. So what that means is, if you use norm.s.dist and you put in 3 times your capability index, and you use true to get the cumulative distribution function, that gives you the probability of getting a failing, an out of spec value. 3 times your capability index is basically the probability of a failing value. Okay, so why 1.33? Well, if your capability index is greater than or equal to 1.33, this is generally considered a passing value. So if we multiply 1.33 by 3 to get the z-score of 1.33, we plug it in to norm.s.dist, and then we take the actual cumulative distribution function of 1.33 times 3, which is 3.99, so basically 4. We get a probability of 0.00003, or 0.003%, or 30 parts per million. So a capability higher than 1.33 means that you have less than a 0.003% chance of an out of spec condition, statistically speaking. So that is 6 sigma. 6 sigma is less than 30 parts per million failing. And we just calculated it off of the normal distribution. That is incredible to me. So I hope this was a great introduction to capability, how they're calculated, and why 1.33. To me, this is incredible. This changed the game on what capability is. I always knew that they were numbers and they must have meant something. But when you sit down and look at the math, you realize that you can use Excel to get the statistical probability of a failing value based on your capability, based on your standard deviation and your mean and your tolerance. To me, that's just incredible. So thank you so much for watching. Have a great day, and please do something awesome.